So, a very good evening to one and all present here. I'd like to welcome you all to today's value-added session of DSA Carnival 2.0 on behalf of CodeChef ADGITM, CodeChef GEC Ripos, and everyone else who contributed to this event. Data structures and algorithms are the subject of this 10-day course, and at the conclusion of each lesson, you will receive a link to an exam. I want to start by saying thanks to the Geeks for Geeks and Coding Minutes to be our title sponsor and education partner. Today is the seventh day of the event, and today's topic of linked list Floyd cycle, detection, algo stack, and introduction to Q. Many people overlook while linked list discussing data structures. It's not a difficult subject, but it is significant. So, Saptrishi Mukherjee, a very renowned educator, is here to help us understand the notion of linked list. He is an SDE at Google, master in Codeforces, and a 6-star at CodeChef. Make the links of your link list concept stronger and let the knowledge of stacks and queue cross the threshold of your amygdala. I'm honored to welcome you, sir. Over to you, sir.
Thank you. I think it was Ritima, right? Thank you for the warm introduction. And let me figure out some way so that I can see everyone's comments. Just a second. Okay, welcome, folks. And I think we should ideally wait for some time uh, till we have folks joining. Shall we? Or shall we rather, keep it recorded? If I'm on the correct link, then I think we are waiting for some folks to join. Right? Anyway, what were the topics that you all are covered in the last few days? I think that they are slightly messed up. I see. So basically, from the first day of the carnival, what I can see is some basics have been covered. Arrays, you all have done. Something around strings, time and space complexity. You had a session on searching, which had linear and binary search. You had sorting, you had recursion. So a number of important topics you have very quickly visited in these last few days. So I think I'll be waiting around 3 to 4 minutes because people are joining. And then we'll be starting on this fresh topic linked list, I think, which hasn't been touched in the previous classes. So as people do join, we will basically get started, depending or rather observing what kind of audiences we have based on whether we have beginner or intermediate audiences, etc. And we'll take it from there. So estimated time of starting is going to be 4:14. I guess by then we'll have mostly the people who have planned to join. So yeah. If you have any questions, you can paste on chat, or if you have anything to ask. Okay, okay, yeah. Thank you for the answers. So, by the way, among the people who have already joined, this is a basic question. Where would you place yourself in terms of the understanding of linked lists and these data structures? I mean, which are not advanced data structures, but slightly intermediate data structures, which comes after the basic data structures. So, where would you place yourself? Are you absolute beginners or intermediates? Or have you solved quite many problems? I want to do CP more, but at what stage in linked list and graph and trees data structures come into question? Come into question as in questions of your Codeforces and CodeChef contests, Arman? Rishabh, this is the only class that I'm taking, so day by day coverage is not pertinent for my teaching alone. This is the first class that I mean, this is the only class that I'm taking in this carnival. After this, we have different classes on the other topics. So let's see what fun we can have in a single day on these quite large topics. Okay. So yeah, Arman, I mean, cover these data structures. There is one theoretical part of it, and then there are practical aspects of it. Learn these things, and then you will have many different questions to practice these things on. After a point of time, this will become quite natural, taking up these topics and practicing questions on them. And by the time when you sit in contest, you will understand that linked list and these topics are not very pertinent for competitive programming per se. But there are topics like stacks and queues which often are handy, and there are mostly algorithms which are very beneficial for solving problems. So anyway, competitive programming comes with a bit of learning and a bit of implementing and practice. These topics will help you more in your um, basic data structures and algorithms understanding and practice. While for computer programming, you have other algorithms which are much more providential. But anyway, these algorithms or these sessions basically provide you a wide view of what are the things available in this field and how you can basically work on a permutation of them, understand what are the different ways in which we evaluate different topics, different data structures, different algorithms, and basically you'll understand that when we have to solve a problem, what are the different ways we think that what is the data structure or algorithm we should apply at that point of time. So those understandings, I think these sessions will help you to gather. And then computer programming comes over with a large number of new things, which if you are into computer programming, you will naturally grasp over the coming days. So yeah, I think it is a good time to start the session. Very good afternoon to all of you present here. I am Saptarshi Mukherjee. I had been introduced a moment back, so I'll not talk much about myself. I'm working currently as a software engineer at Google, and I have enjoyed computer programming over the years. There's a reason I have been in some of these sessions till now. I've been a master at Codeforces, a six-star at CodeChef, and I've been to the ASM ICPC a number of times. That's in short about myself. Um, and today we are going to have some fun around topics like linked list, stacks, and queues. These are topics which, whatever you take interest in, if you are in engineering colleges, by the end of your final year, you're going to study these things at some time or the other. And you will be basically solving problems on them, trying to understand them, trying to rectify your mistakes. And through some cycles, you will be at some point of time preparing for your placements or preparing for some contests or etc. And these topics will always help you in your preparations. So anyway, today's session is not a so-called lecture. It's rather to get you introduced to some of these things, linked lists, stacks, etc., and whatever. And looking at some fun things, looking at how they behave, looking at some mathematical things on how they basically behave. And my intention would be that by the end of this class, you gather sufficient interest to carry on the process of learning after this session goes. Okay, so tell me very quickly how many of you consider yourself as beginner or intermediate in linked list? And if you think that you are a problem solver, then basically you can say, you can call yourself a problem solver in linked lists. if you have already solved some problems. So where would you place yourself? A beginner, an intermediate, or solver? Intermediate, okay. Thanks for being the icebreaker. Who else? What about the rest? Beginner basically means that you have not known anything much about linked lists. And intermediate means that you know sufficiently about linked lists. Two, three questions basically you have solved. Okay. The rest, awesome, thank you. So I've got the basic idea. I'll be starting with a beginner perspective. Then as we scale up, I'll be stepping into Floyd cycle detection, which is one of the main agenda for today. And then on the basis of how much time will permit, we may step into stacks and queues, or we would ensure that you know linked lists quite well. We won't take up topics like stacks and queues unnecessarily at the end. So, okay, we'll start with linked lists, and the agenda goes something like this. We will take the basics of linked lists, and then we will step into some problems, or basically in programming languages, how we deal with linked lists. With some easy codes, I'll basically show you some idea about insertion and deletion in linked lists. And this is something around 40 minutes, we'll be closing these things. Then I'll be directly stepping into Floyd cycle detection. Floyd cycle detection will have some discussion around the basic idea, some mathematics. And what I've planned is after we cover the basic discussion, I'll be stepping into some applications of Floyd cycle detection, which is in cryptography. And yeah, so some discussion around cryptography we'll be having. If you are in first or second year, which I expect you are, we will be, I mean, you might not be introduced to cryptography till now. So yeah, we'll be having it as a fun discussion. It won't be very mathematically deep or mathematically intensive. So yeah, enjoy as much as you can understand and you can feel. So let's get started then. Awesome. So which is the data structure that you all have covered till now the most? I believe the most ubiquitously used data structure till now for you has been an array. What is basically an array? An array goes something like this. Just a second. Yeah, an array basically goes like this. You have a structure. If we talk about arrays, this is a structure which basically has a number of positions, and each of these positions can store a particular kind of value, which can be of a primitive data type, like it can be an integer, it can be a decimal data type or something else. It can be a string, it can be a composite data type as well. So array is such a structure which is the easiest way to think about a container storing a number of items lined up together. So you basically have some length of this array, and you say that the array starts with an index 0 and it continues up to an index len minus 1. These are the indices of an array. So it basically proceeds like this: 0, 1, 2, 3, etc. So what is fun about it, or what is an interesting trait of arrays? If you look at how they are allocated in memory, an array basically always follows a continuous memory allocation. A continuous memory allocation. Have you heard this term? Have you heard this term before? So if you look at your memory, you have some blocks of memory which are associated for some aspects of your tasks. You have a part of memory known as the memory heap, which is intended to store all these information, the values which you place in this container. So in your memory heap, you have, let's say this is your memory heap. By memory, I basically mean your random access memory RAM. So within that, let's say you have these blocks, and within these blocks, you will have these partitions. Each partition will be of some length. Let us say, for now, This array is also having each unit as 4 bytes, and here also I'm referring each unit as 4 bytes. So 4 bytes are needed to store a value of integer type, you all know that. So awesome. So basically we will store all the values over here. If this is array AR, we store the array AR0, I'm sorry, the element AR0 in the first place, and then element AR1 in the next place, and then AR2 in the next place, and so on. We keep on storing these things in the consecutive places. What I essentially mean is that in the memory, all these whatever elements I have written in an array, they are stored sequentially. You don't have one element written over here, another element written over here, and another element written somewhere else. You don't have that. It strongly follows a trend of sequential memory allocation, and you can say that if elements at index 1 is present over here, element at index 2 is present just after that element. This is a strong thing which is followed in array, which is quite different from many other structures which you use from your libraries in your programming language, whatever programming language you are using. So now coming to the question, what is the problem with this? We all know what is the benefit of this. The benefit of this kind of a structure is if you want to go to any particular index, let's say I want to go to index 5, 0, 1, 2, 3, 4, 5, 3, 4, 5. If you want to go to this index, for an array, you don't basically have an address for each index. For each element, you don't carry the address that okay, if I want to access the fifth element, take me to the fifth position, take me to the index which stores the fifth element. I rather say that take me to the place where the array is located, and over there I know where my fifth index is located. So whenever I read that this is my array, I propagate myself to the place where this array starts. I say that this is the base address of the array. You all might be familiar with this term. This is the base address of the array. And then we say that, okay, we are 5 positions away from the starting position. We are basically at index 5, which is 5 positions away from index 0. And hence we say that basically move 5 places in front. 1, 2, 3, 4, 5. We basically move 5 places, and that is how we reach this position. And it doesn't move one space at a time, it doesn't move one place at a time. The movement is pretty fast, you can say. Directly we can move from the 0th index element to the 5th index element. So to some extent you all were familiar with this. So it is such an optimized infrastructure. We call this as an order 1 access. Basically, this particular property that you can access any element in a very short amount of time. Whatever the element is, you know where the element is placed. You just have to propagate to the base address of the array, and then from there you can just take a jump of some k elements, and you will be able to reach the final destination. So this is what we basically call as something like order 1. What did I mention? Memory access, right? Order 1 access. Order 1 element access. This is one of the prime importance or prime utilities of using an array. But there are some disadvantages as well for which today's class or today's session is occurring. What is the disadvantage? Let's say I want to delete the element at index 3. Let us say that I want to delete this index. I want to delete this index. So what happens? Initially, I had AR3 present over here, I had AR4 present over here, I had AR5 present over here, and I had AR6 present over here. Now if I have to visualize the same thing, when I'm deleting this particular element, what this means is that this element is no longer going to be a part of your array. And not only that, the elements which are located after this will come one step back. Make sense? When I delete this element, the elements which are at index 4, index 5, index 6, they will come one steps back. Now when I ask that what element is present at your index 3, it should tell me the element which is present over here. It should tell me x, because x will now come from index 4 to index 3. And if my memory has to handle this, My memory has to do a number of things. It has to say that take all the elements from in front of AR3 and place this AR3 onwards at these positions. So basically, we need something like this. We have to delete all this stuff, whatever are present over here. And we need to say that this is the place from where AR4 all these things will start. So let's say XYZ are these terms, XYZ. So basically X comes over here, Y comes over here, Z comes over here. Over here we had X present over here, Y present over here, Z present over here. But now those X, Y, Z have to be brought one step backwards, which essentially means that if you have 10 elements present after the element which you are deleting, you need 10 replacements, you need 10 swapping, you need 10 movements towards the left. Make sense till now? So essentially, the deletion of elements is not turning out to be very optimized, because if you have to delete an element, deletion is pretty easy. But then carrying forward, or rather fetching the next few elements to the previous position, is a harder thing because it takes more time. And that is the reason we have other data structures which came into the picture, which basically said that to reduce the overhead of memory usage, we have other data structures which don't mandate all the elements to be stored in that order, in those particular positions. If I say that, okay, why are we worrying about AR4? Why are we always pulling AR4 to the previous position? Why don't we let it remain to the position where it is? Then basically we are saying that no longer it is continuous. We rather have to say that, okay, then basically in that structure, let's say this is my structure. These are my places, these are my zones. I'm placing the elements over here, I'm skipping this part, and then I'm placing the rest of the elements over here, something like this. If I allow this, then basically I am allowing the memory allocation to be discontinuous, to be non-continuous. So this essentially means that array is not something that is going to help me out now, because array is not something that supports a discontinuous memory allocation. Why? By its own property. It is by continuous memory allocation that an array can provide me order 1 access, very fast access. But now, because I'm allowing the random access, random allocation kind of a thing, I have to store the address of every element. I need to store the address of every element. Where is every element placed? And if you delve a bit deep into the design of these things in the memory, it is not a very easy thing. Somewhere, basically, our notions, conventions have to break, which essentially means that we somewhere need to go to a different data structure if we want the flexibility of easy deletion, and if we want a compromise to the continuous memory allocation. In simpler words, if we say that, okay, if we want another data structure which basically will not store data continuously, which can store in a different manner. So for that, there will be different properties. Then basically we have to go away from the array and move to a different data structure. What happens then? Then basically this deletion problem that we are facing over here can be avoided. Till now, is everything fine? Till now, are you fine with whatever we have discussed? Based on what you already know about arrays, is it fine? Awesome. So stepping forward, this is what basically it looks like. Fine. Let's say I want something like this. I want some element A, then some element B, and then some element C. These are my 3 elements that I want to store in this order. Or let's say another element D. And I don't want to store them continuously in the memory. Then the memory also allows me some other way of storing these things. It tells me that let's store these things in different positions. Somewhere like this. We will store A over here. We will store, let's say, B over here. We might store C somewhere over here. And we will store D somewhere over here. They are not sequentially placed. And my code has, first of all, an access to a simpler place. It does not have access to all the elements individually. It has access only to the first element. So my code, through some mechanism called the function stack, through the local variables present over there, it has some access to the first variable. But we basically first element. But we basically need access to all the elements. So how are they now connected? How can I get access to the next elements? The memory can have something like this. The memory can have some property like this, that every element will know where my next element lies. So in memory now, basically every element will store two information, its own value and where the next element is located. So this element which is containing A is going to store two things. One is the value A, that this is my value. You are asking me my value is A. A can be 5, 10, whatever. And then it will say that where is the next value, which is basically asking that where is the second element. It will say yes, it is located over there. It will basically give you the memory address of this element of B. What next? So now basically if you give me the address of the first element, I know how to go to the address of the second element. Why? Because the address of the first element, because the first element contains the address to the second element. It stores the link to the next element. And this is largely, I mean, if you are new to blockchains, if you don't know about blockchains, this is how blockchains and blockchains work. And this is basically the foundation on top of which all your Bitcoin, Ethereum frameworks are all working. So at the very lowest level, this is the basic thing, how the nodes are tied together. There is no continuous thing somewhere where things are getting stored, but everyone knows where is my successor. So A knows that there B is located. B knows that somewhere over there my next element is located. So B is storing the address of C. And C again basically is storing the address of D. This is how these elements are connected. And D basically says that I am not succeeded by any other element. So D basically says that I don't have anything in front of me. And this is technically termed as null. Makes sense? So this is the memory allocation that will allow us to ignore the mandatory thing of continuous memory allocation which the array concept has had impressed upon us. We can say we no longer need to keep in mind or keep adhered ourselves to the continuous memory allocation thing. We can basically focus just on the elements, store them at different positions and attach them in some order. So now basically this is in the gist of linked lists. In linked lists we say every linked list starts with some element which is known as the head of the linked list. So linked list data structure is basically a chain of different elements. It is a list of different elements where elements are just linked one to the other. So basically this is the first element which we call as the head. The head is connected to the second element. How? Basically the head contains some value of itself, let's say 5. And then it contains some other link. So you can visualize this like this. A block contains two information. One is its own value. Another is some kind of link. This link stores where my next element is present. It stores the memory address of the next element, or you can say a reference to the next element. So in this way, they are basically connected. You have 10 present over here. And let's say it is succeeded by another element, which let's say is 8. And it may be succeeded by another element, which might be 27, and so on. At some point of time, you will say that there is no other element. This basically is a linked list. We can name this linked lists in any manner. Let's say this is A, this is B, this is C. So what we mean by this is that the next element to head is A. In other words, head points towards A points towards B points towards C, and C points towards null. This is the basic thing about linked list. So now, how does our programming language basically support this? We'll quickly take a look at that. But till now, just convey, it has been around 30 minutes, or I think at least 20 minutes. Is there any doubts that you all have? Are there any doubts? Or are the things clear till now? how we have stepped from continuous to discontinuous memory allocation. Is it clear? Do you have any doubts? Do you have any questions before we step into the implementation part? Awesome. What about the rest? Let me also touch upon that basic thing. What happens if I delete B? What happens if I want to delete B? Can I say in the memory, I can just break this link, and just create this link, and automatically the deletion will be implemented. So can you see now I don't have to work so hard in carrying the elements of B and C and everything after those behind their current positions. I can just say break two links where A is pointing towards B and B is pointing towards C because B is not going to remain. So break the links associated with B and just connect A to C. So if you just do this, if you see the red lines and just forget these two blue lines which I have cancelled, can you see that now A is connected to C and C is connected to D? So very easily, I have just fiddled a bit with the links and I have brought a change in my linked list, which basically tells me that the deletion is no longer a hard thing for us. If I want to delete an element, I just have to break the links and connect the other things. It is something like this. These are some blocks, these are some other blocks. This is a middle block. I'm just saying forget this middle block and attach these two things. That's it. Once you're able to do it, you are done. Your new linked list is there for you. You don't have to worry about bringing back those chains of things behind. So this is the advantage that all of us have met here to learn for. This is the advantage for which arrays have not delved into every use case of industry. So that being the introduction of linked lists, now we will see how we can implement the linked lists. So a linked list basically is composed of nodes. Every unit of a linked list is basically known as a node. So these things that I've basically drawn over here, these are nothing but nodes. Nodes of a linked list. Each of these blocks is a node, and a node contains two things. A node will contain two things. One is its own value, and another is the link to the next element, which we'll call the next. So VAL represents a value, and next contains the reference to the next element. So let us see. By the way, if you want to store in a certain element, if you want to store these two things, a value and the next, what is a data type you can use? What data type will support the storage of these two things, a value and a reference to the next? Any ideas? Pointer will store a reference to the next value, but I have to store the value as well. A pointer will store only one thing. A pointer will store something else. Depending on the data type of the pointer, it will store something else. Pair, yes, okay. A pair is a nice answer. What else? Pointer will not store multiple things. Pointer, I need to store these two things. One is my current value. If you use some integer data type, int a equals to 5, a will store only one value, which is 5. If you write int a equals to 7, it will store only one value, which is 7. If you write pointer int star ptr equals to ampersand 7, ampersand a, so it will basically store the address of a. It will not store two things. Here, if you store the node as a pointer, it will just store the address of the next. It can store, depending on what you want to do, it can store that, but it can't store the value simultaneously. We need to store two things. So yeah, pair is the best answer till now. Pair will basically help you to store two things. One element will basically store your value, another element will store the reference to the next element. So your value, you can say, That's something like an int data type may support. You can also have string, you can have long data type, double data type, float data type, byte, short, whatever you want. I'm taking int as an example because that is the data type which you all have used the most till now. And if we look at next, for next basically, we have to store the reference to the next element. So is everyone fine if I use, if I talk in terms of Java at present? So, I mean, I'm sure there are students present from Java, C++, Python. Let us, for the time being, talk in terms of Java. So, basically, this next has to store the information about the next node. So, for this reason, this next is also going to be of the type that stores this node. In other words, this node has to store two informations, val and next. So, this node has to be some composite data type. This is the first thing. This node has to be some composite data type. And for these kind of customizable composite data types or customizable stuff, we basically proceed towards the data type which is class. We use class data type to store um, these to create these kind of objects which can have any information that we want. For example, I mean, I hope you all are familiar with classes. When you go to a website like Amazon, what do you see? You basically have so many products which are lined up in some order based on the filters that you've applied. So every product, you will be able to see every product give you certain important information. It has some image. It will have some, if you are talking about, let's say, a mobile phone, it will have some battery specifications, it will have some camera specification, it will have the model details, it will have the price, and there will be some information. So the important thing is all the mobile phones have the same kind of, I mean, the same categories of specifications. They have the same titles. Each are having some price mentioned. Each are having some camera details mentioned. Each are having some battery specifications, some display specifications, some glass specifications, etc. mentioned. So essentially, the values are different. From one phone to the other phone, the values are differing. The model number is differing, and those things, the battery is differing, battery specifications are differing. So from there, we can basically say there is a common structure to all of these things. So what there should be something in the back end which basically creates a structure and says that yes, for any mobile phone that you want to add, please adhere to this structure, assign the values, and I will place that in the Amazon page. It works something like that. So essentially, class is one such thing which is ubiquitously used for implementing these customizable structures. So over here also, this node, I want to store two fancy things, which is an integer and a reference to the next node. If I want to store something like that, a class is something which can help me. This class will contain, or the structure of this class will basically store two things. One is the value itself, another is the reference to the next node. And the reference to the next node, by the concept of C++ or by what you have seen in Java, you can say it will be the same class. It will be the same class. So let us write it in the form of a code. So this is how it looks like: class node. Class node. It basically has two things. One is int data. These are the member variables of this class. And what is the next? You have node next. Node next. So what I essentially mean is I am pointing to an instance of the same class. I'm pointing to an instance of the same class. I'm myself a node. I'm pointing to some other node. I'm I'm a student. I'm pointing to some other student. This is basically the idea. So I'm storing the information of some other student, being a student myself. This is how a node basically is working. And now basically every class, as you might have known, what I explained a moment back was basically what a constructor is. I'm sorry, what object-oriented programming is. Every object, every node over here is an object. And the class which basically defines each of these objects, defines the structure of each of these objects, is class node over here. So coming one step forward, what is the next thing we should do? Basically, we should define how to construct this object. We want to construct a node. How should we construct it? We can say using a constructor. So we use something like this. public node, and then we just assign some value int data, let's say. In data, so basically we say that, okay, I've written val above, right? So let's say every node has a val. So we say that to the val, we are going to assign this data that we have passed from our function. And then the next also we need to assign some value. We will say that till now, I don't know what is going to come in front of me. So I will assign null. I will point to null. This is what a simple node is. This is what a simple node is. If you want to see this as a diagram, this is what it represents. A node is this, it contains some value, which we are sending some data variable and assigning that value to that variable. And then this is pointing to something which is being stored as next. Okay, you can say this is being stored as next. So this would be some object of the node class. Object of node class. Object of node class. Fine. So if you are a bit familiar with classes, then you should be knowing this. What happens if I do something like this? Node head is equal to new node 7. What will happen if I do this? Any guesses? I know there is a lag and I can't do much about it. What will this single line code do for us? Arman, from this code, what do you think? When you're calling new node, what happens? This constructor gets called. So no 7 nodes won't be created. Anybody else? What exactly will happen when we call this? This constructor that I've written is a parameterized constructor, which takes a value and creates an object on the basis of the value that has been passed. Very good, Himanshu. Correct, Jatin. Yeah, Arman. Fine. So essentially something like this happens. First of all, from the right you will start. New node 7 is the first thing that will take place. What will new node 7 do? Whenever this new operator is used in Java, this creates something in your heap. This will create some space in your heap. So basically in your heap memory, some node will get created. Some node will get created. And that node will obey the instructions you have passed over here. You will say that for that node, the value will be equal to the data that you have passed. So from 7, can you see? You are passing this 7 to this data. This data value is being written over here. So your value is becoming 7. Now instead of value, it will be basically storing 7. In the place of value, it will be storing 7. And it will point towards null. And it will point towards null. And this will happen in the heap. This happens when this part of the line executes. Okay? From the right, it starts executing. This part happens. What is the remaining part? When I'm assigning it, this is the assignment operator, equal to. When I'm assigning it to something like this, what happens? I'm defining something, node head. Just like you do int a, double b, float c, I'm doing node head. What happens as a result? In my stack, in my memory stack, a variable gets created, and that variable is named as head, and that head variable will now point towards this memory location which stores this particular node. In simpler words, my head will be carrying some reference to this particular element. So my head will basically be at the node which is storing 7. Got it? So this is what this line will do. First create the node and then make the variable which we are assigning the value to point towards it. Fine till now? This is what this particular line of code will do. Okay, so what will we do next? Let us say I want something different. Now this 7 is already there. This is the head. I want it to point towards another node, which is let's say 5, and I want that to point towards null. Already my 7 is created. This is what I have currently. Now I want this 7 to point towards another node 5, and that should point towards null. This second node can be anything. This second node can be, let's say, SEC, something like this. So what can I write? What can I do for this? Currently, I have only 7. So can I say first, let us create the 5 node. Let us create the node which carries 5. So we can do a similar thing. New node 5. This will create for me a node whose value is 5. And then I'll assign it to some variable whose name is something like SEC. Node SEC. So this will create for me another node which has value 5. Currently both are pointing towards null. 7 was already pointing towards null. Will I call this? Just like the previous code, now 5 will also point towards null. Now what can I say? That now basically I don't want this kind of thing to occur. Two things scattered. I want 7 to point towards 5. How do we do that? We know every object has got these two things. A value, a val, and the next. We know these two things are there in every object. A val and the next. So we can say the val we don't have to change. For the node which is having the value 7, we want it to store the value 7, but its next should not be null. Its next should be the node which carries the value 5. So basically I am saying that instead of what is currently at next, I want a different thing at next. Instead of this null at the next, I want this 5 at the next of this 7. I want something like this. Make sense? So can I say if I want something like that, then essentially it's basically about breaking this link and making this link point towards this particular node? Yes or no? And what is the way to do this? Basically we say that this is your node head and this is your node SEC. So head dot next is getting changed. Head dot next initially was null. Now it is getting changed to SEC. And the moment you do this, automatically you get what is lying above you. Automatically you get this thing. Is it clear? Now let's say I want you to print what is the value of the first node. You can print, if I ask you to print the value of first node, you can print something like this. Print head dot val. Head dot val. Because head is an object whose dot val, dot is basically that referencing whatever, dot operator or whatever. That operator which will help you to access the members of this particular object, member functions or member variables or whatever. So head dot val will basically help you to access the member val of this object. If I want to print the value of this head, I can do print head dot val. If I want to print the value of the second node, I can do something like print sec dot val. If I want to print the value of the second node, I can do something like this. Print sec dot val. Or I can also do something like this, print head dot next dot val, something like that. This is in brief the introduction of linked lists. Not in brief, I would say in quite an amount of detail. Okay, so now let's say I have this kind of a node, a linked list, let's say. This is my linked list 5213. This is my head this is my second, this is my third, and this is my tail. Something like this. Now if I say head dot next dot val equals to 8, can you tell me what will be the new structure of the linked list? How many elements and what will be the elements in order from left to right? What will my elements look like when I do this single step? What about the rest? Awesome, very good. So essentially, the way it occurs is this one will not happen from the right, this one happens from the left. So there are certain things which um, are different conventions. So this one you have to start processing from the left. Head dot next will take you to the next element of head. Then dot next will take you to the next element of head. Then dot val will basically say that, okay, let me do it slower. Head basically means over here. Head dot next means the next element of head, means now you're over here. Then dot next means you're going to the next element, which is over here. And then dot val basically means that you're accessing the value of this node which you're currently at. This is your current node. So it's dot val you're now looking at. So the value of this element you're now looking at, you're changing this to 8. Got it? So now your linked list will look something like 5, 2, 8, 3. No deletion of elements, no addition of elements. Basically, we are saying that this object had a val, had a next. We are updating that val. We are modifying that val. We are not adding a physical node. I have not written new node anywhere. So it won't be 52813. It is basically saying that go to this node, access this damn member, and change it from whatever it is containing, which I'm not caring about, to something which I care about, which is 8. It is basically, I mean, frankly, just speaking this, and we are making this change, and we have the 5283 new linked list in front of us. So that is a bit around what we keep on doing with linked lists. Okay. Now, I'll discuss some basic ideas. Let's say you have some linked list. Let's say you have some linked list of size, length. This is null. Now let's say this is A, this is B, this is C, this is D, this is E. What are these A, B, C, D, E? The names we have assigned to these 5 elements. So now tell me one thing. Is there any of these elements from which I can reach all the other elements? From any of these elements, can I reach all the other elements? From D, can I reach all the elements? From B, can I reach all the elements? From A, can I reach all the elements? From E, can I reach all the elements, or there is no such element from where I can reach all the elements of this linked list? In steps, of course, in steps. Of course, in steps. Like over here, from this 5, I have shown like this. Head.next.next is able to take us to this third node. So the same question over here. Very good. From A, right? Why from E? Okay, we'll come to that. But first of all, from A, if you are given the reference of this element A, what do we know? If I do dot next once, I can reach the node B. If I do dot next another time, I can reach the node C. If I do dot next another time, I can reach the node D. If I do dot next another time, I can reach the node E. I'm able to cover all the elements. On the other hand, if I start from E, if I start from the last node, or if I start from any node, does this structure allow me to go to the back? Does this structure contain any reference to the previous element? No. From E, I'm storing only 2 informations. One is its own value, another is next, which is pointing to null. That's it. E doesn't know anything else. E stores only 2 things from the structure that I've written. E stores only two things, value and the next. Next is null for E. So E can't take us behind. In other words, no node of this linked list can take us behind. In other words, a linked list does not have the property that can support a backward iteration, so long as we are talking about this kind of a linked list, which is known as a single linked list. We don't have any way, any known method to proceed backwards in a linked list, like what you're seeing over here. So, yeah, the essence of this idea was that if you have the head, if you have the head of the linked list, you can go to any element of the linked list. In other words, you have the entire linked list with you. If I don't give you the addresses of the other elements, if I give you just the head, you can reach any element in one or two or multiple moves. You can reach any element of that linked list. And that is the reason we express linked list in this manner. We store the head of the linked list and we say that now from here we can reach any elements. So you have the entire linked list with you. You can do whatever you want. Can we define anything for previous link in class node? Yes, definitely we can do it. And if you go to doubly linked list does that. Every node points towards front and right. And you can also store something called random. I mean, you can store anything. It is a class. It is your class. You are making that class. You can store anything. You can store the reference to the previous element to some 10 elements later, some element, or whatever random element you have in your mind. You can store anything you want. You can create your own class for that. But this is the basic class, which when you are often asked to solve a problem of linked lists, you are expected to use. This is a basic, template, that every element stores only the information about one element in front of it and its own value. So using that, this is the structure that we basically follow. This is singly linked list. There are many questions in which you will find that doubly linked list, which is having pointers on two sides, has the same efficiency as a singly linked list. For example, blockchain doesn't have a doubly linked list. Blockchain are specifically focusing on Bitcoin. The Bitcoin framework doesn't have a doubly linked list. Every node is pointing to only the next node. Initially, you have the Genesis block. From the Genesis block, in the Genesis block, basically all the initial transactions, etc., are there. Basically, that is how every block is being pointed to by its previous block, and the longest chain becomes the blockchain. Those are the other things. So every block points to the next block. That is how it occurs over there. I'm sorry. The next block points towards the previous block only. So basically, every block says that I am the child of that block. So it's basically the reverse of this. And at the beginning of Genesis block, which is pointing at nothing. So in this way, every block points at only one block, which essentially means pointing at all its parents as well, indirectly, transitively. So yeah, not going over there. The version that you mentioned is about doubly linked list, where we have pointers on both the directions, this direction, this direction. Okay, that is a doubly linked list. But when you don't have those pointers, you have a singly linked list. And a singly linked list is what I basically mentioned. Using a single head, you can access all the elements. So in practice, we only give the head to the coder and ask him to iterate through the entire linked list and do whatever he wants to do. If it is a searching problem or something else, basically according. Yeah, fine. Thanks for the question. Okay. Now tell me one thing. If I want to add an element over here, if I want to add some element x over here and point that x towards A, then how much time will it take? How can I add this? This is known as insertion at head. Any guesses? Very good. Awesome. We just have to say create this node x, and then x should point towards A, and then x should become the head. These are the three steps. What are the three steps? Create the node x, X should point towards A, that is x dot next is equal to A, simple, and then head equals to X. What happens when you do head equals to X? Remember, head is located in your stack. Head is just a name. X is just a name. A, B, C, D, E are all names. These nodes are physical entities. When you say head equals to X, this basically says that currently the A was the head, but now that I'm saying head equals to X, it basically gets changed. This understanding is important when you do a number of problems and when you get stuck in languages like C++ and Java. This understanding is a bit necessary because when you pass some variables, let's say when you pass head to a function where the head gets modified in some way or the other, whether the change will get reflected in your um, caller function, it depends on that. But I'm not going to that depth. For that, you can maybe practice a bit and see how basically Java handles this pass reference by value kind of thing. So for now, let us keep it simple. X will point towards head A, and then head basically points to X. So I will say that now head is no longer X, head will now be at, I mean, head is no longer at A, head will be at X. If I write head equals to X, it will do that thing for me. And that's it. So insertion of head will occur in these three steps, which is order one. Which is order one. Now let us talk about the second thing. What if I want to insert at the tail? Which means I basically want to add this over here, this X, and point it towards null. Point it towards null. Just a second. Yeah, point it towards null. So how much time will this take? You are given only the head. You only have the head, which is A over here. Sorry. You have only the head over here. Right. From the head, one by one, you need to travel up to the length, up to the last node of the linked list. And from there, you can say that yes, I have reached the last node of the linked list. Now I can change my tail. I can say, okay, create that new node X, and then this current node dot next is equal to X, and that X is already pointing towards null, so we will be done. So the important thing is from the head, you have to gradually move forward and come to the last node, which is E. And from that node, you basically need to point towards the new node, which is X, which itself is pointing towards null. So the insertion at tail will take how much time? The length. The length is the bigger thing. It will depend on length. So n plus 2 steps, we discard the constants and those things. So it is order n. Okay. And if we want to insert somewhere in the middle, we will say that, let's say I want to insert after C. I want to insert after C. So you will say, okay, go up to C. From C, change the next to this node. And before you change, store your next node because you still need that. Store your next node and make this new element point towards the next node. And that's it. Insertion and middle will also occur very quickly, but the only thing is you have to travel up to this middle node, after which you want to insert the value. So yeah, that is pretty much how it will look at. Is the insertion in linked list clear? If I give you a linked list and if I want you to make small changes in terms of insertion in middle, beginning, end, will you be able to do it? I'm not discussing codes. Definitely in the first few iterations, you will struggle a bit with codes, but we'll keep codes away because 2 hour session won't allow everything, or 1.5 hour session, I think, won't allow everything. So I'm keeping that away, but conceptually, is it clear? Is it making sense? Awesome. So proceeding forward. The next thing that you all might get to do is deletion. If you want to delete a node, you basically have to travel. Let's say I want to delete D over here. Let's say I want to delete D over here. I'll come to it, Arman. I'll come to it. Let's say I want to delete this D over here. What does that mean? I want my final linked list to look something like this. I will have this node, I'll have this node, I'll have this node, and then this C will point towards E, and I'll have this E, and then I'll have this null. So everything will remain the same, only D will die out. So can I say that basically C was pointing towards D? If I want to delete D, then basically the previous node of D, which is C in this case, needs to change its next element, needs to change its next to point towards not D, but the next element of D, which is E. Can I say something like this? So can I say these are just three steps? One is reach the element before the element to be deleted, before the element to be deleted, element to be deleted. Let's say that is C. The element to be deleted is D. And then what will we say? Forget who is to the next of you. Who is to the next of you? That is E. Who is that? Basically, that is C dot next dot next. So you will forget who is to your next. To your next, you will place whoever is at your next. So whoever is at your next, you will assign that to this particular element. That's it. And you're done. So now your C will point towards E. Now if you start from head, after head you will get B as you got before. After B you will get C. After C you will now get C dot next. C dot next is nothing but E. C dot next was E. E got assigned to C dot next. So now C dot next will take you to E. So after this, basically the linked list looks like this. Basically the linked list looks like this. This is null, and this is the same D. This is your head. This is A, B, C. This is E, and this is D. So from the main linked list, we have been able to omit the element D. Are you all clear that after this particular line of code, this is somewhat what your linked list will look like? Is this making sense? Is this making sense? Awesome. So I know there is a lag, so bear with me as I am bearing with this. The thing is, D has not been deleted. D has not been deleted. But so look over here. From the head, can you reach D? Not really. From the head, you cannot reach D anymore. C was pointing towards D. Now C has forgotten D. C has abandoned D. D is saying that I'll remember you. Who cares? You can remember whoever you want. If I don't remember you, I can't reach you. And that's what we need. In our linked list, I need 4 elements to be stored. I need to delete the element B. If I am not remembering element D can basically point anywhere it wants, but I'm not storing it in my linked list. So if you talk about Java, this is one of the reasons I've chosen Java, and I choose Java whenever I talk about linked lists. If you speak about Java, Java has a very good garbage collector. Whenever it will see that there is a node whom no one is referencing, whom the head is not able to reference, who does not have anybody pointing towards it, the node will say, the collector will basically collect that as a garbage. The garbage collector will run and take that because nobody is referring to it. It is equivalent to getting lost. Nobody is storing that node. For understanding it in depth, you have to slightly get into how they are actually stored in heap and how they are pointed to by elements in stack. But for the time being, remember this, that if from the head we cannot reach an element, it is as good as considering that element to be not present in the linked list. So after this, whenever you will study linked list, you will see that nobody is bothered about removing this stray element because this element is unreachable. So we can say that this linked list is as good as the kind of linked list we wanted to achieve by the deletion operation. So our deletion basically wanted us to reach the site of deletion, change the pointer, and that's it. So if we have to delete some element x, we are deleting, we are going to the parent of x. From there, we are changing the link. We are not going to the successor of x, we are not going to x itself, we are going to the parent of x, saying that you are pointing to this unwanted thing. So it is time that you forget this unwanted thing and point to the wanted thing, or rather the important thing which is existing after the unwanted thing. So we'll basically have to reach the node which is before the element to be deleted. These are some small things that you have to remember, that you have to conceptually think before you proceed to code, and then you have to start coding. The implementation will be pretty straightforward once conceptually you are clear about it. But whatever basics we have discussed till now, are you all clear with that? Are all of you clear with whatever basics we have discussed till now? If you delete the first element, you just have to do one extra thing or one different thing. If you are deleting the first element, you need to say that just make the second element as the head. Just make the second element as the head, no other changes, etc. If you want to forget A, let's just say that B is the head. That's it. Okay, yeah. So fine. And if you want to delete the last element, just go to its parent and say the same thing. So if you tell D the same thing, that D dot next equals to D dot next dot next, what happens? D dot next equals to null, so null will get assigned to D dot next, which is fine. We are fine with that. So if you want to delete E, it is nothing different. D dot next will become null, which is exactly what we wanted. So yeah, with the given logic, we can't delete the last node, right? We can delete. This will support. That's what I mentioned. We can delete the last node. What will happen if A is pointing towards B, B is pointing towards C, C is pointing towards D, D is pointing towards E, E is pointing towards null? We will say you want to delete E. You want to delete E, so we are saying go to the parent. Go to the parent of E, which is D. So we will do D dot next equals to D dot next dot next. Exactly this. D dot next dot next. And what happens? What is to the next of D? What is this D dot next dot next? D dot next is E and E dot next is null. So basically, this is what this RHS is. So what can we say? That now D dot next will become whatever this entity is storing. So this entity is storing null, so I will say D dot next will now store null. D dot next will not store anything else. D dot next will now store null. So yeah, A to B to C to D to null is exactly what we wanted, and that's exactly what it is storing. And E will also point towards null. Don't ask same null or different null. Null means null, nothing. But then how linked list insertion and deletion is better than arrays insertion and deletion? It depends on the problem. It depends on the use case. For certain problems, if let's say I tell you, for example, for implementation of stacks and queues, let's say for implementation of stack or for any situation, whenever I tell you, I just want you to remove the first element always. I don't want you to remove the last element. I don't want you to remove anything else. I want you to remove only the first element at any point of time. Then what can you say? You can say, yes, deletion is order 1 for me. I can just go to the next node and declare it the head. That's it. My linked list is modified. But if in an array I tell you to delete the first element, can you see what is the cost overhead? To change the array, you basically have to copy all the n-1 elements to one step behind. Okay. So that is how with the given, yeah. So that is basically the use of linked lists. And let's say if I give you the address of D over here, and if I ask you delete its next node, there are such use cases as well. Then what will D do? D will basically say that I'll forget this E. I'll forget this E very easily just by pointing to something next. That's it. Okay. Stack array will be helpful. Stack array will be helpful. It depends on how you're implementing. The implementations are different. If you don't adopt the circular mechanism, stacks are quite easily, can be quite easily implemented using linked lists. Linked lists are actually They can be used to implement stacks. Today we won't get the time to discuss that, but you can see how stacks are used to implement linked lists. If you understand what we are discussing today, it will be quite easy and interesting for you to understand how stacks are implemented using linked lists. Okay, so it is for those use cases, and also there are other kinds of customizations we can do in linked lists, by which you can even do binary search in linked lists. Okay, in binary search you need order one index, order one access, which we cannot do in linked list, but we store indices in different manners, we store references in different manners, you can do it using that. In order n log n space you can basically do the binary search over n logs. Okay, so yeah, any other questions before we proceed into Floyd cycle detection? For now, whatever questions you have, keep them in your mind till the day you implement these things. This has got many uses. For example, when you do undo redo, your operations, whatever editor, etc., you're using, they are all chained. They are all occurring in a chain. Some operation, some other operation, they're all in a chain. You say that, okay, please take me back along the chain. I want to see where I was 5 steps back. You press Control Z 5 times or Command Z 5 times. And then you basically say that, okay, now I want to get to 3 steps after this. And then so you will press the redo thing, which can be Command Y or I don't know, Command Shift Z or whatever, Control Y, whatever. So you will press the redo button 3 times or whatever number of times. That will take you to the step which is 3 steps ahead of you. So in this way you can roam around, and linked lists are very useful for these situations. Then suddenly you say that, okay, now I want to do a different operation. Whenever you do a different operation, all the redo steps get cancelled. All the things which are in the redo thing, they get forgotten. So the linked list, this garbage collection is very easy. It basically says that, yeah, take care of it. It will be taken care of immediately. So much of RAM will no more be consumed. So yeah, there are use cases. There are many such use cases actually. Okay. By the way, any other questions before we proceed to Floyd cycle detection? So Anurag, can we keep the class up to 6? Shall we keep the class up to 6? I don't know what is the usual limit, but is that going to be a fair thing, or whoever is present over here?
हाँ जी सर, अगर आपको सही लग रहा आप कर सकते हैं, वरना तो फिर जैसे आप कहें।
I see.
अनुराग भैया बोल रहे हैं।
Yeah, sure.
Yeah, sure, Saptarshi sir. You can go ahead like till whenever you want, and till when audience wants. We don't have an issue.
Let's fix it up to 6. Okay. So we have seen the basics of linked list, and now once again conceptually we will proceed to to the better detail, which is slightly more complicated than these things, slightly more interesting, more convoluted than these things. We will proceed to the stage where we find cycles in linked lists. Let us see how cycles can be generated in a linked list. Okay, yeah, thanks for the compliments. Let us then get started. Cycle in linked list. So just like your original linked list, you have a head. And one important thing you must keep in mind, there are different data structures and there are different abstract data types which are based on data structures. There are some fundamental things. One is what properties of access, deletion, insertion you're having, and how you're storing the elements, memory allocation, etc. Another is linearity or non-linearity, these aspects. Linked list is purely linear. Can you see over here? All the structures we are doing are linear. And an element always points to one direction, which is in the front. So you can basically arrange them in a line. They will always point to one direction. So linked list is always a linear thing. Just by the very definition of how we are customizing or framing these things, framing the class. But now let us take one step ahead and see if this line continues to grow, what possibly can happen. Let's say we are having some nodes. We are having some nodes, and then something like this happens. This is also pointing towards some other node. And there you go. So before this was fine as a linked list. If I would have said that this is now pointing towards null, you could have actually said that yes, this is the linked list we have seen till now. It is going in a straight line. I have drawn it in a curved manner. That is my problem. But the linked list in the memory is not having any convolution as such. It is going straight up to the last node. But now if I say that this last node, let's call it as x, this will not point towards null. This will point towards this node. I can store it. Yes or no? Based on what my data type supports, I can store it. I can say that this last node is going to point to an already occurred node. We were coming in this way, and then this last node is pointing towards this node. We are not violating anything till now. Every node is still having two things, one value and one next. Each element, can you see? Each element is having only two things, one value and one next. One value and one next. One value and one next. Here also one value and one next. So essentially, I'm not violating the basic property of linked list. Now coming back, this is a special thing which we can observe in a linked list. And when this thing occurs, we call this a cycle. And when a cycle occurs, we can't draw any more nodes now. We can add any more nodes in between two nodes. We can do that. We can add some node over here. We can add some node over here. We can do these things. But we can't extend the linked list anymore. We can't add any node in the linked list from the tail kind of thing because there is no tail. If you start iterating from the beginning, what happens? From the head, if you go next, what happens? You are going next. And basically, as you proceed, you will come over here. You will proceed in steps. You'll proceed in steps, you'll proceed over here, and once again, you will carry on the journey over here. Infinitely, it will continue moving in this cycle according to the next pointers. Can you all visualize this? Can you all visualize this? That if a cycle occurs, then in steps, they will keep on moving in a cycle? Yes or no? From the head, if you start iterating, awesome. So now, the thing is, you have to find whether there is a cycle or not. You have to find whether there is a cycle or not. So from the beginning, if you start iterating, and if you iterate the entire linked list, and when you come back to this node, you are iterating in this way, you are iterating in this way, you are iterating. When you come back, you should say that yes, there is a cycle. Right? So if I ask you that, is there a cycle in this linked list? How would you approach the problem? How would you approach the problem? The thing is, you can keep on moving. If you don't do the checking, you can keep on moving. You can keep on moving if you don't have any precautionary check. But how can you detect if there is a cycle in a linked list? Any ideas of data structures which can help you? Any ideas of logic which can help you? Can I say if I store the information of all the nodes? Correct. Hashmap has said yes. A node address will be repeated. A node address will be repeated, or you can say if all are of distinct elements. If I say that the linked list, in every linked list, each element has a distinct value. You can say I can basically store all the values. At the moment I see while I'm moving, if I see a value is repeated, or if I see a node is repeated, if I see I'm visiting a node which I've already visited, automatically I can say I can find it. I found a cycle. If the essence of the argument is that if there is a cycle, then you have the chance of coming back to an element. after moving through the cycle. You started from over here, you started from the head, you proceeded up to here, and then you rotated across the cycle, and then you have come back to the same element. So essentially, this is the difference between a cycle and a non-cycle linked list. In a cycle, when you iterate, you are revisiting an element. And in a linked list, in a chain, in a line, in a non-cycle, acyclic linked list, when you basically iterate, where there is no cycle, you are not repeating any node. You're only going forward. You don't have the possibility, you don't have the tools to revisit any node. So revisiting is only possible in the case of cycle. So that will be how we'll be checking it. Are we revisiting any node? So one way is that you use something like hash set. Something like hash set. What is hash set? Basically a structure which stores some values. So we can have a hash set which will store nodes, which will store the nodes. Hash set node. This will contain a repository, a dictionary of all the nodes. Every time I visit a node, I will say put it in the hash set. And when I visit a new node, I'll basically ask, is it there in the hash set? If it is there, that means I've visited it before. If it is not there, put it inside and please proceed next. So in this way, I can figure out that basically this is the first node which will be rotating, which will be revisiting. When I come from the head up to this node and then proceed across the cycle and then visit this node once again, this is the node which we are repeating. So awesome. Easy thing. We can use the hash set, which is going to store these keys for us. And yeah, we can come to that node and infer that there is a cycle. What is the space complexity? What is the space complexity? Awesome. So it possibly can be that you have to cover n by 2 nodes. Even if you have to cover n by 2 nodes, just a second. Sorry, you have to store all the nodes, right? From the beginning till the end, you have to store all the nodes. And then you can reach this node and then you say that, okay, in whatever nodes I have stored, this element is present. So whatever, I mean, you can optimize your space as well. But order n space is something which is coming through easy thinking. That we will iterate through all the nodes till we reach this node, till we revisit this node, we would have visited all the nodes. And if we are storing every node, the space complexity is order n. The space complexity is order n. And space complexity is something which you really don't care about. Because you have, most of you have not faced the problem of space exceeding your constraints. If you are writing a program and the program takes 2 hours to run, you can still bear with it. Okay, let me wait for 2 hours, let me chill around and come back, and it will be basically finishing in some time. But what happens if it consumes not 2 hours, but some 2 petabytes of space? It is, forget your own computer on which you're watching this video or your own device on which you're watching this video. You can bring some significant structure, some significant computational structure down. So basically, space is a very important thing. If your task is going to put pressure on RAM as it grows, as the space grows, as the nodes are growing, then it is not a question of efficiency or trade-off of time versus space. I mean, it is just about feasibility in the first place. If your RAM is 16 GB and you want to put on it a burden of 32 GB, it's not something how it works, unless the SSD and those things have a good handshaking with your hard drive, etc. I'm sorry, with the RAM, etc. It will not basically help you. So in basically the essence of the discussion is space complexity, though is often neglected, is not something that we can neglect every time, because these things, whatever are being passed to your head is being passed to you. The entire linked list is not being passed to you in a RAM. So somewhere, if you iteratively proceed through it, that will not put any pressure on the RAM. At any point of time, you are only at a single node. But if you store all of them in some hash set, that will put pressure. Order and space complexity is not a good option for that. So essentially, what I mean is we have to optimize the space complexity. Definitely, we have to visit all the nodes. If you have to visit all the nodes, the time complexity can't be better. But we have to reduce the space. We can't store so many nodes in our repository. We can't store so many things. Rather, instead of storing, we need something to tell us that when are we able to reach, or when are we revisiting a node, or are we revisiting any node? As we are proceeding, are we revisiting any node? We need to find that out. So for this, we use some tortoise and hare approach, or slow pointer and fast pointer approach, which I'm going to explain in the next few minutes. But is the basic idea clear? What we have discussed till now about cycle and linked list and what we are going to discuss now onwards, is that basically clear, or do you have any doubts? Yeah, visited array is the same thing. Node address repeated. Yeah, you can store the address, same thing. Address and reference are two different things, so it depends on you which one you want to use. It's the same thing. So anyway, tell me if it is clear. Awesome. What about the rest? Is it good to proceed from here? Okay, so let us take it from here. Awesome. So now we do it in this way. We basically say that let us keep a slow pointer and let us keep a fast pointer. We will start the slow pointer. S is the slow pointer and F is the fast pointer. S is the slow pointer, which we start with head.next, head.next. And F is the fast pointer, which we start with the next of head, which is head.next. And in this way, what happens? My S starts with the second node, my F starts with the third node. And I will say both of them that their task is the S should move one step at a time. S should move one step at a time, and F should move two steps at a time because it is fast pointer. It should move two steps at a time. So if there is no cycle, can I say S and F definitely won't meet? F is in front of me. Let's say I walk at 1 meter per second. Somebody is in front of me who walks at 2 meters per second. Will I ever be able to catch him? If there is no cyclic thing in our trajectory, if he is proceeding forward and I am also proceeding forward in a line, will I be able to catch him ever? No. If I am at a slower speed and the person in front of me is at a faster speed or at a faster pace, definitely I can't catch him. But if there is a cycle, then there is a possibility that I can catch him. Rather, the possibility is that he will be revolving across the cycle and catching me. Let us see how that happens. So S is first positioned over here. Let me use S1 for the first position of S1 and F1 for the first position of F1. Or to keep it different, let me use the same ink. F1 I'll write above. F1. So now what is the next step of S1? S1 will go one step forward. So S1 goes here. This is S in the second move. And F1 in the second move, it will be present two steps in front of it. So it will be present over here. This is F2, second position of F. Then S will move to its third position, which is next one, S3. And F moves two positions, which is here, F3. Then S moves to one position, which is here, S4. And F moves to position, which is present over here, F4. S moves one position, which is S5. F moves two positions and comes over here. This is F5. 5. S again moves here and it becomes S6, and you can see F5 will now move to its next dot next, so it will come over here. It will now become F6, basically the sixth move. After the sixth move, F and S are in the same position. Could you all follow this? At every step, F is moving 2 places, S is moving 1 place. So after 6 moves, S and F are in the same place. Can you all see this? This is the node where they are all meeting. So can you see, because we have a cycle, we say don't store anything, don't remember anything. Just start 2 pointers, instruct 1 pointer to move 1 step at a time, and instruct the second pointer to move 2 steps at a time. After 6 moves, what happens? S has covered 6 nodes and F has covered 12 nodes. F has completed the cycle and met the place, met the slow pointer. F has completed, first pointer has completed the cycle and met the slow pointer. So this particular trick has worked for us. We are basically saying that the fast pointer will always jump at a higher speed and the slow pointer will jump at a slower speed. In this way, the fast can complete the cycle and meet the slow pointer. So when the cycle gets completed and it meets it, we can say yes, it can definitely meet if there is a cycle. Only if there is a cycle, it can meet. If there is no cycle, it cannot ever meet. So through this inference, without storing anything, we have not stored any of these nodes. Question mark, what is the question? So essentially, we have not stored any nodes. We have basically asked the slow pointers and fast pointers to move forward. If I once again show how they are moving, first of all, this is where your slow pointer is. This is where your fast pointer is. Next step, your slow pointer comes over here and your fast pointer comes over here. This one vanishes. Next step, your slow pointer comes over here. Slow pointer comes 1 step forward and fast pointer comes 2 steps forward. So it comes over here. This is where your slow and fast pointers currently are. Now you'll say your slow pointer comes over here and your fast pointer comes over here. Got it? The next step is your slow pointer comes over here and the fast pointer comes over here. Now you can see both are inside the cycle. The slow pointer and fast pointer both are inside the cycle. What will the slow pointer now do? 1 second. Have we missed a step? 1, 2, 3, 4, 5. There it is. 1, 2, 3, 4, 5. I think I missed a step. So by this time, slow pointer is basically present over here, and fast pointer is present over here. What happens now? Now basically, slow pointer is trying to enter the circle, and fast pointer has not yet entered the cycle. Fast pointer is already inside the cycle. So fast pointer is moving through the cycle and slow pointer is entering. This is where we have a chance that they can meet. And that is eventually what occurs. So slow pointer comes over here. Fast pointer moves 2 steps in front. And then the next step, this is where the slow and fast pointer currently are. Fast pointer is just behind the slow pointer. Now slow pointer will move 1 step and fast pointer will move 2 steps. And what you observe is 2 steps from here, from fast pointer, and 1 step from the slow pointer basically land up to the same destination. And yeah, that's what Floyd's cycle detection algorithm basically helps us to calculate. Basically it helps us to infer. If there was no cycle, they couldn't have met. But since there is a cycle, they are able to meet. They are able to meet somewhere inside the cycle. Because one thing is there, if they enter the cycle, they can't leave the cycle. So there is something in this cycle due to which they are not able to leave. Because they have entered the cycle and there is some pattern in which they are moving. So the first one is just stepping into the slow one, and that is how we are able to make them meet. So yeah, any questions till now? Did you understand the basics of this? Did you understand basically what we are speaking about? What these fast and slow pointers are doing? Awesome. So now the question is, I hope the rest are also clear. So now the question is, which might be there in some of your minds also. Yes, Binod, very good, very good. So coming back to it, what is a guarantee that it will always work? First of all, is it guaranteed that at some point of time, slow pointer and fast pointer will both be inside the circle, inside the cycle? After some moves, both slow and fast pointer will be inside the cycle. Once they enter the cycle, they can't leave it. So after some point of time, both the slow and fast pointer will be inside the cycle. Yes or no? Yes or no? Right. So from there, when they are inside the cycle, when they are inside the cycle, focus on this. This is your cycle. This guy, let's say this is the slow pointer. This is moving at one move per second, something like that. One move per second. And this fast pointer is moving here at two move per second. Can I say that this fast pointer is approaching the slow pointer by one move per second if they move in this way? The fast pointer is approaching the slow pointer at a pace of one move per second relative speed. Let's say I am moving. Let's say I am moving and somebody else is also moving. I am moving at 2 meter per second and I'll make myself the faster now. Somebody else is moving at 1 meter per second. Can I say essentially I'm approaching him by 1 meter per second? I'm coming closer to him by 1 meter per second, which means if there is 5 meter distance between us, can I say that in 5 seconds I'll be able to meet that guy? If I'm moving at 2 meter per second, if that guy is moving at 1 meter per second, this is basic relative velocity computations, etc., which we all have done in our intermediate. So this is the idea that when basically they two are going at their own pace, here M means move. Every step, the slow one is moving by one move per step, and the fast one is moving by two moves, and the fast one is actually approaching the slow one. So can I say by one move every time it is coming closer? So if the distance between these two are currently something equivalent to 5 moves, can I say in 5 steps the fast one will be catching the slow one? They will come to the same place always. If there is a distance of 5 between them, what happens? After 5 steps, this goes forward by 5, this goes forward by 10. So as it goes forward by 10, it is compensating. I mean, it is covering this 5 plus this 5. So it is essentially this. If this is, you all might have understood this. Still just, yeah. Let's say this is your slow pointer, fast pointer, and this is a slow pointer. He is approaching at 2 steps, 2 moves per step, and this is approaching at 1 move per step. Now there is 5 meter distance or a 5 move distance between them. 5 move distance. So what can I say? What happens after 5 steps? After 5 steps, this will move 5 steps over here. This distance will be basically 5 steps. This distance will be 5 steps. And what happens from this fast pointer? 5 into 2. This is a velocity and the time is 5 seconds. So this will move 10 steps. 10 means 5 plus 5. So this will also land at the same position. This will also land at the same position. Got it? So the person over here and the person over here at these respective speeds, after 5 seconds will be at the same finishing line. And that is essentially what we are doing over here. Whatever is the length of the cycle, the fast and slow pointer are coming closer by one step, by one move per step after they have entered the cycle. So we just have to wait for how far they are. After those many steps, they will definitely meet. Is it clear? Is the idea clear? This is the intuition of why always the cycle detection algorithm will work this way. Is the idea clear? Is the mathematical thing clear? Awesome. Awesome. Any doubts? Any questions? Okay, looks fine. We'll come to a question after this. Let us address that question. What if my slow pointer moves by one space at a time and my fast pointer moves by 3 spaces at a time? What happens then? What happens if the slow pointer moves by one place at a time and the fast pointer moves by 3 places at a time? What happens then? So I will start my slow pointer at head.next and I will start my fast pointer at head.next dot next dot next. What else? For this I will say one step or one move at a time, and for this one I will say it will move 3 moves at a time. Will it be able to give me the cycle? Yes or no? What do you think? Will it be able to give me a cycle? Last year I took the sorting session, sorting and some other session for, DSA Carnival 1.0. And I remember I had asked the same question. In merge sort or binary search, whatever I covered then, I asked that instead of dividing in 2, what if we divide in 3? What happens? It was a similar question, and the answer you can go back and look what it was. But over here, is it possible or not? If the slow pointer moves by only one step at a time and fast pointer moves by 3 steps. 3 steps at one go, not one by one. 3 steps at one go. Will it give me the cycle? Will they always intersect at some place or will they not intersect? If they intersect, then I know that there is a cycle. If they don't intersect, then there is no cycle. Can I say that? What do you think? Why, Jatin? Why do you think no? What about the rest? Okay, Vinod. There is a problem over here. What problem is there? Let's say the cycle is of even length. I will not discuss each and every case, but let's say the cycle is of even length, something like this. Let's say this is the cycle. So you are entering over here, this is the entry point into the cycle, and then this is how you are proceeding. Let's say there are 6 nodes in the cycle. Here you have the fast. Here you have the slow. Now what happens? According to the agreement, according to the argument that we had given, the fast pointer is at how many distance away from the slow pointer? 1, 2, 3, 4, 5. The fast pointer is at 5 distance away from the slow pointer. It needs to go 5 steps to reach the slow pointer. Yes or no? So if I would have said that the fast pointer is moving forward by 2 steps, slow by 1 step, I know that okay, relative step is 1. So in 5 steps, they will meet. But over here, 1 move at a time and 2 moves at a time. So what is the difference? Fast is approaching the slow by how many moves at a time? Can I say 3 minus 1, 2 steps? Can I say the difference is going to be 3 minus 1 equal to 2 steps at a time? 2 steps at a time? Yes or no? So your friend has got it. So essentially, they are nearing. They are nearing by 2 steps at a time. Nearing, or basically the difference is changing by 2 steps at a time. And your difference is 5. So what happens? Basically, when this S was behind F, F is in front of it, the difference is 5. From 5, what happens? The difference becomes, after the next step, it becomes 3. The relative distance becomes 3 because by 2 steps they are coming closer. Then it becomes once again. When you bring them closer by 2 steps, it becomes 1. The difference becomes 1. Then you again bring them closer. You get something like minus 1. What does minus 1 indicate? That the fast has come ahead of the slow point. The fast has not intersected. So when it was 1, the fast was over here and the slow was over here. They were pointing towards each other. But now you said slow will move forward and fast will move 3 steps forward. 1, 2, 3. 3 steps forward. So what can we see? That fast is overtaken now. So now the fast is present at 1 step in front of S. Minus 1, in other words, you can say it is 5 steps behind S. 1 step ahead of S or 5 steps behind S is the same thing. So I can say it is minus 1, or basically 5 steps behind S. So from 5, if I again continue, it will again continue doing something like this, 3, 1, and so on. It may not be true for other cycle lengths, or it may not be true for certain other situations, and I'll leave that as a kind of case study for you. In some situations, this may work. I don't know. To know this, we just have to look at it in the same way. So I'll leave that for you. Have fun with that. I hope this basic idea is clear. It is not a magic that they are just coming to the same place. They are coinciding, and we have to obey that. We have to sort of blindly follow that. Basically, there is this mathematics working underneath it, and that is why they are meeting. So that's essentially this. Now, a last thing. Sometimes we are not only interested about whether there is a cycle or not, we are also interested about what is the starting node of this cycle. What is the starting node of this cycle? So basically, after we have discovered the cycle, I want you to find out that this is the starting node. They are intersecting over here. Keep in mind, they are intersecting over here. This is the node they are intersecting at. But I want you to find which is the starting node of this cycle. What is the starting node? The node at which the outside chain is able to enter the cycle. Should we conclude with this discussion? Shall we conclude with this discussion? What do you say? What if we have to find the starting node? We don't have any information from the cycle. We can't query outside. We can't query the chain outside because we can't go behind. From the chain we can enter the cycle. From the cycle we can't enter the chain. So we can't ask the chain that are you connected to me over here, or are you not connected to me? We can't ask that. So let us address that now. How can we possibly find out the starting point, starting node of this chain? This will be the last topic of discussion for today before we conclude. There you go. Now let us come to this. Yeah. For this, we basically say, now that we have come over here, now that we have come up to this node, let's call this as x. From x, let us start moving forward at the slow pace, one move at a time. And from the head also, let us name it as y, we'll start moving at the same pace forward. What did I say? First, we will find out the intersection point where fast and slow are coinciding. Then from there, our new journey will start. We want to find out this ticked node, the node that I've ticked. I want to find out that node where the chain is basically coming into the cycle. That is the entry point of the chain into the cycle. So x and y, what we can say is, let's try to move them by one step at a time. So what happens? These are the first positions, y1 and this x1. Then one step later, this is x2 and this will be y2. Then we have x3 and this will be y3. And then we have x4 and this would be y4. And then we have x5 over here, this would be y5. And then we have x6 over here and this will be y6. Can you see x and y are intersecting at the starting node? What have I done? Let me reiterate myself. I started one pointer from the head and one pointer from the intersection point of the slow and fast pointer. I started two pointers and slowly I'm moving both of them one by one. They are meeting at the starting point. Can you all see this? That they have met at the starting point? Why this has happened, we don't know, but somehow it has happened. Can you all see that? Are you all clear about what we wanted to do and we are able to basically do that? Awesome. So now the only thing left is, will this always come? Will this always come to the same place? Let us look at that last thing. Will this always bring our pointer to the starting point? We'll discuss that. For that, I'll need some variables. So let us say there are, how many? Let's say there are A nodes before the cycle. Let's say there are A nodes before the cycle. And let's say there are B nodes from the start of the cycle till the intersection point. Okay, so I'll mark this as the intersection point. From the start to the intersection point, we have B nodes, and after the intersection point till the beginning of the cycle, I mean the rest of the nodes. So we have taken from the start of the cycle up to intersection point as B nodes. B is a number of nodes there. And the cycle length minus B is going to be C. C is the remaining nodes. Okay. So let me mark it once again. Let's say this is a chain. And this chain, it is starting a cycle over here. And this cycle is continuing and ending over here, let's say. And this is the node where we are meeting. So I'm calling from here to here these many nodes as A. From here to the intersection point, these many nodes as B. And from here to the end, don't take this node in consideration, don't take this. Just before this, name this as C. Now tell me. Now tell me something. This is the node I. The thing is, as soon as the slow pointer enters the cycle, the fast pointer starts approaching it. Okay. So before the slow pointer, here we are talking about the initial approach. Slow equals to slow dot next, fast equals to fast dot next, that thing. So the thing is, as soon as the slow pointer comes into the cycle, fast pointer starts approaching it. And mathematically you can prove it that before the is L included, is L or I? No, I is not included in C length. B and B plus C equals to cycle length. Okay, B plus C equals to cycle length, and B contains both I and the mouth of the start of the cycle. So let's say this is the start, this is S. So B includes both S and I. Okay, and C does not include either of them. So now the thing is, when the slow pointer enters the cycle, from that moment only fast pointer starts approaching it. So slow pointer, mathematically you can see that the slow pointer is unable to complete even one cycle. Before it completes one cycle, because the cycle is of length b plus c, and the distance between fast and slow pointer is less than b plus c. So in less than, I mean, whatever steps are there, in that many steps, that node will be able to catch it up. So essentially, your left pointer, where was I? Your slow pointer will have covered how many steps to move up to this node? Let me do something, just a second. Okay, let me change the convention a bit. So I will take B up to before the intersection point. Okay, this is just for the ease of calculation. I'll take B up to here, and I'll take C up to for the remaining nodes. I'll take C for the remaining nodes. So here also I will take B from here to just over this, and C I'll be having it as included. C I'll have it as included over here. Fine. So B includes S and C includes I. So to reach from head to I, how much time will it take to reach from head to I for the slow pointer? How much steps will it take to reach from head to I? For the slow pointer, how much time will it take? How many moves will it take? This is B. What do you think? First, A moves will be required to enter the cycle. Then B moves will be required to enter the intermediate node. So can we say, very good, can we say this A plus B? A plus B is the, right, A plus B is the number of moves needed by the slow pointer to reach that I. And we know that the same number of moves is needed by the fast pointer to move from head to I. Once again, head to I, by taking some cycles. This is for the fast pointer. We know that basically, just a second. Yeah. So A moves first, then the cycle length, the fast pointer might move across the cycle some number of times. So what is the cycle length? B plus C. So we can say something like K into B plus C. Plus, after this, what will it do? After it covers this length, it is present over here. After it covers, it comes A distance, and then it covers the cycle a number of times. It is present at S. So now we can say it now needs to just move B steps to reach I. If it moves only B steps, we can say this is a number of times fast pointer. Just a second. Number of times the fast pointer is moving. The distance that fast pointer is moving. The distance that the fast pointer is moving is this, and the distance that the slow pointer is moving is the left one. And what do we know? That the slow pointer is moving at slower speed. So if we count the number of moves number of moves wise, I can say twice the number of moves of the slower pointer matches the number of moves of the fast pointer. If the slow pointer has moved 5 steps, the fast pointer will have moved 10 steps by now. The fast pointer is somewhere over there, k is some number. Got it? We just have to basically solve it. We have to see what comes out of here. Let us see. Let us try to see. 2a plus 2b. 2a plus 2b is equal to a plus b plus k b plus c. So first of all, you can say a is equal to, take 2b over there, what do we get? K minus 1b plus kc. So what do we get? K minus 1 b plus c plus c. What does this give us? Can I say k minus 1 into cycle length into length of cycle plus c? So the number of steps that they have taken, or basically now see what is the relation between A and C. From here we can say, if I start a pointer at the very beginning and if I start a pointer at this I, if I start a pointer at the very beginning and if I start a pointer at I, this will take A times to reach this S. Okay, and in the same time, what will this node do in at the same pace? A is equal to some cycle length plus C, some multiple of cycle length plus C. So can I say, when I'm covering the A length over here, if that many steps I take for the other pointer as well, I'll essentially rotate through this cycle some k minus 1 times, and then I'll proceed C extra steps and I'll be reaching this position. Come over here. I'm starting one pointer to my left, to the head of the linked list. Another pointer I'm starting at the intermediate node. By the time the left pointer reaches the start node, can I say this node, this intermediate node, from there the pointer will make some rounds, some cycles. It will make some cycles and it will be able to reach C extra nodes after the cycle completes, which means it will basically revolve across the cycle up to and come back to the intermediate node, and then from there it will take C extra steps, and by taking C extra steps it will reach S. Does it make sense? If I draw it cleanly, what I have written above is, you have this chain, you have this kind of a chain which is forming a cycle, and you have found that this is where they are intersecting, and you have found that the distance from here to over here is C, and you have found that the distance from here to something over here, basically the distance to reach this position, is A from here and C from there. A from this head and C from the intermediate node. Yeah, I was just thinking that C includes this. C includes this, just a second. C includes this. C includes this. So the distance is C over here and A over here. And what is the relation? What is A minus C? A minus C is equal to some cycle rotations. So when they start, first A minus C duration, what will happen? This will complete some cycles and come back to the same place. And then it will take C strides over here, and from somewhere over here, it will take C strides and they will meet at the same place. And we can get that from the equality above. Basically, the number of steps from head to the starting point is equal to the number of steps from the intermediate node to the starting point plus some cycle iterations. So those cycle iterations will happen. So if we start some pointer to go through this A distance and some pointer to go through the C distance, they will eventually meet. That is the entirety of this topic. Does it make sense? Have you all got some idea? Cycle length. With the given example, k minus 1 equal to 0. K minus 1 equal to 0. Yes, correct. With the given example, k minus 1 is equal to 0. But if the chain before is very long, and the cycle is relatively quite shorter, then it will be just the opposite. I mean, k will have a large value, quite larger value. So yeah, these are all the mathematical things. If you study in the most genuine manner, there is nothing to learn. There is nothing to memorize in the entire thing. So anyway, if you have any last minute questions, we can discuss that. Else, I hope that a decent part of it has sunk in whoever of you have attended most of it. So I hope you have enjoyed it to some extent. This is Floyd's cycle detection algorithm. I wish to talk slightly about the cryptography aspect of it, how it is implemented, and some part of it. But looks like we have to find some other session for that. But anyway, later on you will study yourself. You'll get to know those things yourself. Let us keep it up to here. This has been some decent amount of content for those of you who have been introduced to linked list for the first time today. So yeah, just a second. Yeah, thanks to those who have been till the end. And no, we are not having any next session per se for this DSA Carnival. But anyway, you all can study on top of this. A number of things are there in linked lists and all your other stuff in trees, etc. You can keep on looking at them. You can look at binary search in linked lists and binary search in trees. You will have many other things which take these things as fundamentals. Quite some time later, you will be facing a very good problem of least common ancestor in a binary tree quite some time later when you have grasped the intermediate and advanced stuff, and then you will really like coming back and seeing how the linked list thing has actually supported your understanding there. So anyway, keep the basic things in mind. Sure, it was my pleasure. Yeah, the next session for the DSA Carnival, which will be taken, I think, by Umang or somebody else, is tomorrow. So yeah, it was nice interacting with you. I think Anurag, etc., we are done. And yeah.
Thank you so much, sir, for enlightening us with your knowledge and experience. It's a pleasure for all of us to be taught by you, sir. Thank you, sir, for giving your valuable time and sharing your knowledge with us. Also sharing some extra time with us for the extra knowledge. So there's a special thanks to the Geeks for Geeks and Coding Minutes for being our title sponsor and education partner. Now, it's the time for your quiz, guys. The link will be in the description box given below, so check it out. Winners will be given exciting prizes, so what are you guys waiting for? Hurry up. Thank you so much.
So you think you know data structures well, but often get stuck when it comes to problem solving. Well, now you are at the right place. Welcome to Data Structures and Algorithms Level Up course. Hi, my name is Prateek and I'm a software engineer at Google. I have created this course for anyone who wants to learn how to apply data structures for solving coding problems and algorithmic optimization. In the past 5 years, I have taught over thousands of developers through my online and in person bootcamps that helped many students and working professionals in their careers immensely. This course will help you to develop a strong problem solving mindset and write cleaner and highly optimized code. This course is a highly practical course, and we will discuss over 100 problems of varying difficulty levels along with a complete hands-on implementation. You will learn various tips and tricks related to concepts like recursion, backtracking, sliding window, two-pointer problems, dynamic programming, pattern matching, graph algorithms, and more. Not just that, you will also learn by solving problems involving various data structures such as stacks, queues, linked lists, heaps, hash tables, tries, and graphs. With over 200 plus high quality video lectures, concise and simplified explanations for complex topics, this course is your one stop destination to master problem solving. Unlike most other courses, this course is fully interactive. You also get coding exercises and multiple choice questions to test your skills. The code judge ensures that your logic is correct and you get a real time feedback on your code submission. Doesn't matter whether you have a computer science background or not. This course is for anyone who wants to ace problem solving and achieve big. So what are you waiting for? Sign up today and I'm looking forward to meet you in the course.